Okay guys, today's lecture is about spread footings. We're going to cover the design of wall footing, single column footing, and combined footing. This is what we cover here in reinforced concrete. Is about shallow foundation. Nothing is deep foundation like what you're supposed to cover in foundation design, which is as you technical or of course you join as a technical elective. So we're going to cover reinforced concrete footings that are considered spread footing or shallow foundation. So we will cover a wall footing, single column footing, and combined footing. Okay. And if you look at the foundation, usually it looks like that. If this is the one at the bottom here, is the property line. That's the property line in here. Okay, that means this is your land. This doesn't belong to you. It's to your neighbor or someone else. And in your building, there is a wall in here. Okay, and for this wall, you can make. You have no problem. You have some room from here. That's a plan view. You're looking at the plan view. That's the wall here, and this is the footing of the wall. So when you design a wall footing, basically you are finding the width and the depth, because that footing will be continuous along the length of the wall. So the loads coming on the wall footing will be per foot strip. So whatever load per foot strip you have, how much the length? So your footing kind of will be 1 foot by the width. Okay? And depth. So again, when we say design, the word design, we're talking about always the cross section in beams, B and H, and the reinforcement. Here in the design, let's say for a single column footing, we will be looking for the area, the depth, and the reinforcement in each direction. That's what we need to design. So you may have a column somewhere in here, an interior column somewhere in here, another one, the column lines like what you have in the project. So for this column, if you want to create like a single column footing for this column, you may not be able to do that because this is not your line. And we always look for the column to be concentric in the middle of the footing. The column must be concentric in the middle of the footing, so that what it's considered pure axial loading. So the columns must be, or the resultant, if it's combined footing, the resultant must be within the center of the footing. Okay? So what you do in this case, you combine this one with the nearest column, such that the resultant of the forces, the axial on this one and the axial on this one, is in the center of the footing. The resultant. Okay? We're going to study how we calculate that. For this one, you will have no problem doing square footing. Sometimes, if you don't want to do a square footing, sometimes you are narrow with the width. You are fixed with the maximum width that you can go. Let's say you cannot go more than 6 foot. So your single column footing will be rectangle footing, 6 by whatever you need it. We're going to see how we calculate how much the required area. Sometimes we do this combine. We can combine something like that. Okay, we do this. Okay, combined footing. If you have two columns that are close from each other, and you calculate the required area for this one as a single column footing, and the required area for this one, and they already they intersect, you do just one combined footing for both of them. You can combine them in one footing. As I told you, the resultant must be in the middle. Remember, the load on each of them is different. The load can be different. So you talk about the resultant to be in the center of the footing. Sometimes we can combine something like that. It's called strap footing. We connect them together, something like that. Usually, this is the case when you have like a moment frame, okay, or concentrically the X bracing. So you like this frame to work together and resisting the lateral load. So you try to tie those footings together after you design the required footing for each of them. So this is called strap footing, combined footing, single column footing, wall footing. All of this one is called spread footings. There's something called mat foundation. Mat foundation. You have the mat or the footing all the way underneath on the entire area of the structure. There is a rule for that usually. When the sum of the areas of all the spread footings here exceeds 70% of the area of the building, is more economical to go with one mat foundation for all of them. And that can be designed by finite element analysis, or can be designed by some approximation by taking strips. Whatever column lines you have, whatever column on that one, take one wide strip for that one, and you just flip the foundation, it becomes like a slab with columns. And the distributed load on that foundation is the resistance from the soil. If you flip the footing, it becomes like a slab. If you flip the slab, it becomes like a footing. Okay? So that's what's called mat foundation. There's something sometimes called slab on grade. You know slab on grade? Any slab that has continuous support, continuous base underneath it, that's slab on grade. It's continuously support. It will not curve. Okay? It will not curve or deflect. Okay? Usually there is a minimum reinforcement and there is specification for the thickness. There is in any building, usually once you build your footing here, and usually we tie the footing together so that we have integral foundation at the top. Once you reach the first floor level in the United States and many other countries, they have mat, small slab on grade 4-inch. 4-inch at the first grade, at the first floor level. It ties all the columns together, and this slab, the 4-inch slab, is very powerful and strong in resisting any lateral load or earthquake loading, if there's an earthquake loading. Okay, so usually once you come to the level, you level your surface, that's the level of the first floor, the entrance, if you enter anything, there's a slab on grade of about 4-inch. And the reinforcement usually there, minimum for shrinkage and temperature. That's just for connecting the columns at the foundation level. Okay, connecting the column at that level. So what we're going to design, we're going to learn how we design the wall footing and single column footing and combined footing. That's what we will cover in here. Okay? That will give you all the basic requirements or basic fundamentals about spread footings. I'll start with the wall footing. So usually you have a wall. If you look at the cross section in the wall, that's your wall. There is a load coming in the wall. If this wall is load bearing, means the load is supporting the slab. The load is supporting the slab. Sometimes these walls are not load bearing, they just carry their self weight. Sometimes they are not load bearing. This information will be given to you. So in other words, the load on that wall will be the self weight for whatever number of floors on top of that wall. It means the slabs are resisted by beams. Sometimes on the edge, because the walls are on the edge. The walls are on the edge. They are carrying load. And we calculate the load per foot. So the load here will be specified by kg per foot or kilonewton per meter, dead and live. So this information will be given to you. Dead and live and any other thing, if there is any other loading. So this load will be resisted by foundation like that, or the soil pressure. Okay? So in our design, what we are required to do is to calculate the required B, the width, and the required edge. B and edge. Okay? That's what we need to come up with. And from edge, we know D equal edge minus the cover, because we use D in our strength calculation, in our flexural design. Same as beam. It's like beam design in here. equal. So how much the cover according to the ACI code? Clear cover over the reinforcement of 3-inch minimum. The ACI call for a clear cover of 3-inch. That's the clear. So the cover to the center usually 4 to 4.5 inch. 4 to 4.5 inch. Okay? You can take it 4 inch if you want. So it will be H minus the cover. The clear cover required over the last part or the closest part to the soil is 3 inch. Why the cover is high in foundation? Because there are sulfates and some other contaminants in the soil. This may come into the bars and make corrosion. Okay? So usually clear cover according to the ACI code is 3 inch. So if you want to take D roughly, either H minus 4 or H minus 4.5. Okay? So now, how are we going to design? Remember, this is the wall continue. Okay? The wall goes like that. So what I'm designing here, what I'm trying to calculate or show you, that we're trying to design 1 foot strip. Okay, this one. And that reinforcement within this one will be all the way. So if the load is applied here, how this one will bend or deflect? The load is coming from here, and this is coming from here. So it's gonna do that somehow, just for right? So that's how it's gonna curve. It's not gonna curve in the wrong direction. It's so long. So there is no bending in the wrong direction. There is bending in this direction. So how is the reinforcement supposed to be? The main steel for bending, is it in the short direction? According to this. So that's where is the main steel. And it's at the bottom, because tension at the bottom. Okay? These are your bars here. Okay? And they have to be at the bottom. So we need to design for those based on bending. The reinforcement there is based on bending. We will check shear, but we don't provide also stirrups in the foundation. So the concrete or shear support. The thickness of the footing must give you enough PVC to resist the shear, the ultimate shear at the critical section. Okay? So now what do we do? Do we put any reinforcement in the wrong direction? Which is typically, from whatever you learn, the information you learn so far, you know, always need a minimum reinforcement. Either there is a value or shrinkage and temperature. So this is the shrinkage and temperature reinforcement. What's AS and T in footings, in split footings? In slabs, how much it was? 100? 1.8, right? Here 1,002 BH. Same. Over there we multiplied by BH, but it was 10018. Now it's 1002. That's in the wrong direction. What's raw minimum for this one? Is raw minimum for beams. Remember raw minimum for beams, guys? Who remember raw minimum for beams? Which is 3 square root of prime C over Fy, or 200 over Fy, which you're going to get the number for F prime C equal 4 KSI, you will get 10033, right? But it depends on Fy. The second value, 200 over Fy, when you buy 200 divided by 60,000, you will get 10033. The first one depends on F prime C. As you increase F prime C, become controlling minimum reinforcement. That's the minimum for that. That's the minimum for that. So when you calculate raw here from the bending for this steel, you check that against raw, as I said, 10033 or 3 square root of prime C over Fy. Good? Okay. So how about D? D need to be checked, again, need to be used in the flexural calculation in the steel here, and need to be checked for shear. Remember, PVC equal what? P 2 square root of prime C B D. B D. Okay? So we need D to check that. This must be greater than greater or equal V U bar U at the critical section. Must be greater than V at the critical section. Where we take the critical section? Typically, when someone is telling you, where? At where? D from face of wall. At D from face of the wall. Look, what's the assumption, guys? I'll try to make it big. We assume this wall is fixed here. So it's like the footing is a cantilever from the face of the wall. The footing is a cantilever from the face of the wall. So this is the cantilever beam now. Likewise from here. So we design one. So this is like fixed here. Why? Because this area is confined with the compression coming from here. I know there is something like that. So this will is like fixed here, and this is a cantilever going up. So the moment here, the maximum moment here will be, if this is W, if this length is whatever, B, any length, call it L here, the maximum moment here will be for a cantilever is WL square over 2. So W here times this length square over 2. That's the maximum moment here you use to design for flexure. For shear, what is the critical section? At D from this. At D from this, which is basically this. This is the section. This is the section. This is the pressure, the soil pressure. Okay? This is your D. Your V at D. This is your V. Basically this. Remember, we are doing for 1 foot strip. 1 foot strip, because the pressure will be specified per square foot, so it will be multiplied by 1. In the wall footing. Is it obvious? So this is what you need to check here. Or you can get D based on that. Get D based on that. And once you have D, calculate the reinforcement. Calculate the required reinforcement. Okay, guys? I will just solve example. Again, this is the easiest footing is a wall footing. We'll work out this example, then we will go into single column footing. We have dead load on a wall equal 12 kip per foot. Live load equal 8 kip per foot. F equal 4 KSI. Fy equal 60 KSI. Okay? Design a wall footing for the given load. So we have a load, we have a wall, and the linear foot of the wall, we have 12 kip dead load, we have 8 kip per foot live load. The bearing capacity of the soil, or the allowable capacity of the soil, Q allowable, equal 4.5 K SF, kip per square foot. Level of footing is 4 feet below grade. By the way, just one more information. Typical wall footings, 1 foot, 1.5, 1 foot. That's typical thickness. But we're gonna check it. But if you want to start the first assumption to check, assume 1 foot. Okay? You know what I'm saying here? So the Q allowable is the bearing capacity of the soil. You know where we get this from? From Gerard office. The guys go and they do the profile and they get whatever soil characteristic and they tell you the bearing capacity at 1 foot is that, 2 foot is that, 3 foot is that, and the type of the soil they have. Then they say, okay, this is a good foundation from the experience at 4 feet or 5 feet. There's that type of soil, rock, some good bearing capacity of that much. So this comes to the structural engineer from where? From the soil report. You sleep a lot because the guys here, they use a factor of safety of at least 2.5. The factor of safety there is 2.5 to 3. Okay? Sometimes goes to 5. So there's a huge factor of safety in this value that was given to you. Okay? You use this Q allowable to find the area, just the area of the footing. So the area, the first thing you calculate is area. Area. A equal del plus Y divided by Q allowable. You see these loads here? Service loads for calculating the area. Why? Because there is a huge factor of safety included in Q allowable. You don't have to magnify the loads for the area only, the area. I'm not talking about the depth or the reinforcement. So the area of the footing is calculated from the service loads. Del plus 5 over that one. Sometimes if you have lateral load like earthquake or wind load, the ACI code allows you to increase this one too by 33%. It allows you to increase this one by 33%. Or del plus 5 plus wind or del plus 5 plus E earthquake divided by 1.33 Q allowable. The larger one. The required area is the larger one. So that yes, they allow you to increase that, but you have more load. Okay? Usually this is what you have. These are service loads, as I said. These are service loads. So now you have the area. Now you have the area. Okay? In our case, the required area is what? A equal what? 12 plus 8 divided by 4.5, which is, what's the answer? 4.44 feet square. What's this area equal what? For the wall footing?
That's per foot.
B times 1. So this is B times 1. So what's B? Required B is 4.44. How much you want to go with? 4.5? Absolutely fine. If you went with 4.5, absolutely correct. You want to go with 5, that's fine too. If you increase the width, if you have room on both sides to increase, you will require lesser reinforcement. Okay? You will have more reinforcement. But we're going to use 4.5 foot. So that's the first item. That's the first item. Okay? So we have B. Once you calculate B now, you calculate something. Is it working? Yeah. By the way, I made a mistake or something need to be subtracted, right?
The top one.
What's that? We said the level of the footing will be where?
4 feet.
At 4 feet. The level of the footing will be at 4 feet. So above that, so that's the foundation, then there is 4 feet on top of that one. There is the thickness of the footing and there is soil. Okay. You have two options. You have two options. Either you add that as a load to this load here, or you subtract that from the bearing capacity. Because this will bring pressure on the soil, right? So the area between them is mixed with concrete and soil. How much? 4 feet. Let's assume one of them will be concrete, right? So how much? The weight of that 1 foot concrete up per square feet? 150. So there's 150 PSF or 0.15 KSF, K per square foot. Go ahead.
Isn't the soil on top gonna help with the
Add more weight.
Yeah, but it's not gonna bend as much.
But it would strengthen.
Yeah, but it add weight on it.
Oh, no.
No, we assume the soil is flexible material. Time. Okay? Okay. So there is 0.15 kip per square foot from the concrete. And then we have 3 feet of soil. The question I should ask you, I don't know, ask you or someone else. What's the unit weight of soil? 100?
It's like 66. In English or metric?
Did we deal with metric?
No, in soils, all we do is metric. We haven't done any English.
In pound per cubic foot. If you take 1 foot container, cube, you fill it with soil from the dirt behind your house, you put it on the scale, how much do you think? Is it, look, common sense. Is it going to be heavier than concrete? Of course no. First of all, it's lighter. Second of all, there's a lot of voids within the soil compared with concrete. So it will be way less than 150. You may say, okay, how about it's going to be like the same as the aggregate, coarse aggregate, right? We did the bulk unit weight of coarse aggregate. You remember that container? You filled it in 3 times, rodded or non-rodded. You put it on the scale. If you take 1 foot cube of sand or coarse aggregate as is, not one of the concrete, you put it in the scale, how much do you think?
98.
95, 100, 105. It depends on the size of those. That will determine the void. So the soil, let's say 100. Sometimes got saturated, maybe a little bit more if it's saturated with water. But if we assume 100, okay? So you can say minus, plus, you add to that 3 times 0.1. Or sometimes you take an average. If you have like the depth of the foundation at 5 or 6, you don't know what the thickness of the footing is going to be 2 feet or 1 feet or something like that. You say, you know what, I'm going to multiply that depth by 0.125 or 125. With an average unit weight of concrete and soil. That's a good conservative number, 0.125, if you want. So now, this Q equal Q allowable minus 4 times 0.125 if you want to do it this way, or you can do 1 times 0.15 plus 3 times 0.11 if you want to take it 110. But this is usually common practice. How much you get? You get 4.5 minus that number. Q equal 4.5 minus this number. 4 exactly. 4 kip per foot square or KSF. What do you want to call it now? What we are doing? Effective. This is the effective for supporting the load. This is what's effective. Part of it went to support the soil and the self-weight of the footing. Okay? Again, as I told you, you can calculate those as weight and add it to the dead load if you want, the self-weight and the weight of the soil. So this is Q effective. QE, U effective. Now this will change here. This will be 4, and you give me this number in here.
5.
Exactly 5?
Well, it's 20 over 4.
Yep. So that's 5. We're going to use 5. And I told you, don't be afraid. This number in real life, some guys, you believe it or not, this is like 12. 12 or 20. 12 or 20. Okay? So that's our B. So I have 5 feet. Now, I need to add something here. Assume width or thickness, wall thickness equal 12 inch or 1 feet. So this is given information for you. So already designed before you come into the foundation. This is 12 inch or 1 feet, thickness of the wall. Okay? So what's this distance from here? From here to here. This from here to here. This cantilever. How is it 1.5? All of it is 5. To the center is 2.5. Right? So this is 2. So this is 2. 2.5 minus half. Okay, guys? 2. That's the cantilever length. That's the cantilever length. Okay? That's the cantilever length. So what's this one Q now here? You think this is Q effective? What's this pressure up? So the load is coming from the wall. We have it. What's this one now? Now we want to design. We're going to do strength design, right? We want to calculate how much this steel needs to be here. And the shrinkage and temperature in the other direction. To do that, when we say strength design, usually what do we use? Service load or ultimate load? Once you have something like that, after that, what do you do? Ultimate load. So P ultimate equal what? 1.2 times 12 plus 1.6 times 8. You get what do you get? 27.2 Kelvin per foot. We know that everything is per foot. We are designing 1 foot strip of the wall footing. Now, what do we do? Now remember, so far we have 2 Q's. Q allowable from the soil guide. Q effective at the level of the footing, subtracting the weight of the soil and the self weight of the footing. Now we need a Q for strength design. We're going to call it Q, what's this? P ultimate. We're going to call it Q ultimate. And Q ultimate equal P ultimate divided by the actual area you use. Divided by the actual area dimension you use. Sometimes you need like 4.5 by 4.7. But you picked 5 by 5. So Q ultimate will be P ultimate over the used area of the footing. So this will be divided by 5 times 1 or 5. So Q ultimate will be how much? 27.2 divided by 5.44 per foot. So that's your Q here. This is Q ultimate equal 5.44 per foot here. So now you are looking for what? The moment here, I'm ultimate at the face of the wall equal what? Q ultimate times this length square over 2. It will be 5.44 times 2 square over 2. Right? 5.44 times this length from here to here, which we said is 2, which is usually this one is 5 minus the width of that divided by 2. 5 minus 1 divided by 2. Good? The moment here, it's a cantilever, guys, cantilever. Fixed cantilever with distributed load. W. You used to have it the other way. This moment here equal W L square over 2. This is W and this is L. In our case, L is 2 and W is 5.44. How much you get? 10.88. Okay? Foot. Per foot. We know that. We're designing one footstep. So that's the moment. That's the moment. Keep it for now. Keep it for now. So what's V ultimate? What's V ultimate? Where we calculate the ultimate? Here. Where we calculate the ultimate? At D. At D. Not 1 actually, we're going to do it in a minute. If we assume D or assume H equal 1 foot. As I told you, this is a good start. This is a good start with that from experience with the wall footing, which is 12 inch. This how much typically will give you D equal, how much do you think? We said, look at this, we said the cover above this bar, is 3 inch, right? The cover above this bar is 3 inch. So how much do you think the cover to the center of that bar? It's not 4 actually, to the center. I know I said 4 for the single column footing, I'll tell you later why. But in this case, how much do you think? Are we going to use number 8? That's a huge size, right? Number 8. Let's say we're going to use number 8. Half of that is ½ inch, right? If this one was number 8, which is big size, good size, to the center of that will be 3 plus ½ inch. So D in this wall footing will be approximately 12 minus 3.5. Again, I said 4 or 4.5. I'll tell you why. Because in the single column footing, we will have 2 layers. 2 layers in each direction. We calculate D for the most critical one. So you have to subtract D plus ½ D in there. You're going to go to the second layer, the top layer. So you're going to have 3 plus the diameter of the bottom layer plus half the diameter of the top layer. That's why I said 4 to 4.5 there. For now, you just look at it. You just have 1 bar. To the center of that, we're going to take 3.5. Okay? So our D is 8.5 or 8 inch. In this case, what's V value here? Or V ultimate here? This one will be Q ultimate. If I take a cut here, Q ultimate times this length, which is 2 minus that. So Q ultimate minus 2, 8.5 over 12. You change it to foot. This will give you how much? Eight and a half divided by 12 minus 2 times 5.44. 7.03 Kelvin. So that's the shear, the ultimate shear. Now check if that thickness D is good. So check PVC equal 0.75 times 2 times square root of 4,000 times 12 times 8.5. Don't forget that 12, multiply by 1 foot for the wood strip. B is 12 inch. Remember, this strip here, 12 inch. Okay? This one will give you PVC. How much?
In inches or feet?
That's in Kelvin. PVC shear strength. Divide by 1,000.
Oh, I see. 9.7.
9.7 Kelvin. Greater than 7.03. Greater than 7.03. Okay. You're going to say this is too much, right? If you want to say this is maybe, I can still decrease the D. That's fine. Remember, the footing in terms of concrete is not expensive. Doesn't need forming. So easy for the concrete thickness. And 10 is good for to accommodate the covers. Remember, you need a cover 3 inch from here and 3 inch from here. From the top. If there is bars on the top. Usually we have some bars too, so we can tie them together, tie the wall rebars there. So you don't want to go less than that in any footing, 12 inch. Sometimes if it's really minor wall that just around the house to carry itself, you may go with 8 inch even. It's small. Okay? Okay? So now we're good. Let's assume someone will say, you know what, I'm going to use H 10 inch and decrease this one. That's fine, but remember, increasing D will save you some steel, right? Increasing D will give you more strength in moment, so it will save you some steel. This is good. This is good. And you have this one like 20 compared to 7 or 10, change it. Remember, if we are talking about like 20 inch thickness, 22 inch thickness, but the 1 foot is typical practice in wall footing. If the first assumption for another design was like, assume D equal 20 inch, and you get something like that, you want to say, you know what, I'm going to bring D down to 18 inch, and check it. So you see, the best practice for footing design is assume, check, assume, check. Some guys may say, keep D as a known here, and a known in this one, and try to make them equal to each other and calculate D. Just assume and check. It's just one simple equation. Okay, guys? And you have a common sense about the assumption. Okay, guys? So we are good. So shear is checked. When I tell you check shear, that's how you check the shear. Now, M ultimate equal what? 10.88 kept foot, right? Equal times 12 equal phi r b d squared. Have you seen something like that? Okay. M ultimate equal phi r b d squared. So this is in kept inch now. This is in kept inch. Those will be in inch. Equal to about 1,000, right? So 12,000. So I have it in pound inch. Now this unit is in pound inch. Because R listed in that table is in PSI, in the design aids. So this equal 0.9 R, what's B? B in here? 12. What's D? 8.5 squared. You do that, you will get R equal 10.88 times 12,000 divided by 0.9, 12, 8.5 squared. You get 167 PSI. Go to the design aid and get me rho for that. Again, remember the other day, last lecture, I calculated using the typical method for the reinforcement. You can go with phi as Fy d minus a over 2 and check A with the iteration method. Or do that. From the design aid, you will get rho for this R. You go with F prime C equal 4, Fy equal 60, and to your best, give me the closest A. Austin.
I've got 175. It's between 0.003 and 0.0025, which is below room.
So for what? Wait.
For 147, it's 0.0025.
160 something. Oh, yeah, I see what you're saying. Okay.
And
You
for
mean 174 or what?
147, rho is 0.0025.
These are the values of R, right?
Yeah.
What's the next value for R?
175.
So ours is 166, 67, sorry. So if you do that, he said, this is what? What?
0.0028.
And this one?
Oh, no, I was interpolating. That one's 0.0025.
Here?
Yep, and then the other one is 0.003.
Yeah, that's equal.
Okay. Both of them, as he said, are less than rho minimum. equal, row minimum equal 3 square root of 4,000 over Fy or 200 over Fy, which is 60,000. So this gives you 0.0033, and this gives you 0.0034 or 32. You know them. This is from even the design yet. You have them in the design yet, or you can calculate them. So these are less than row minimum. We use row minimum. By the way, row minimum, which one is the largest of those? Of course. Row minimum is the largest of those. That's the minimum you can use. Equal 0.0033. Now what's AS? AS equal what, guys? Rho B D. Anytime you calculate rho, this rho is fluctual. This rho is calculated based on strength. It's not the shrinkage and temperature. Okay, not the shrinkage and temperature. It means it's multiplied to calculate AS from this row. You multiply by BD. The shrinkage and temperature you multiply by BH, which is A gross. So this is 0.0033 times 12 times how much? 8.5. Your AS will be
0.34.
0.34. Wait a minute now. What's that number now?
Inch per foot. Inch square per foot.
Each strip, each 1 foot, that's how much steel it needs. You go to the table and you give me what spacing that will give you that. What spacing of a given size that will give you that?
3, 3.5.
Number 3 at?
3.5.
That's so close. Try to
Number
read it.
4 is at 7.
So we have the options. We have number 4 at 7. What's A? AS equal how much?
0.34.
Exactly?
Yeah. That's what I did.
Perfect. The closest. If you can get the closest, the first one above it. Remember, the tables give you for full number. If you want something for a half, like at 7.5, you can get it.
This has half.
This it has half?
Yeah, this has half.
It gives you up to 12, right?
Yep.
If you want more than 12, I told you how you do it, right? When we were there. So that's the reinforcement. So this guy will be, this here will be number 4 at 7. Even our D is stronger, so we're good. Our D is more than 8.5. So we have, that's a safety. That's a safety. That will give you more moment and better shear resistance. Now how about this steel here? This steel. In the wrong direction, longitudinal steel, AS equal 0.002 times what?
Well, for D8.
I'm calculating how much steel we need in the wrong direction. This is what I'm going to do and you explain it to me. In the wrong direction, I'm saying, in the wrong direction, I'm saying AS equal saying it's 0.002 times 4.5 times 12 times 12. You said it's pH, right? This needs to multiply by A gross. I want to calculate how much do I need in this area. All of it. I don't want to take per foot. So I'm trying to calculate how much do I need in all. You can do it per foot. But I'm trying to calculate how much do I need in everything. So I took the cover 3 inch and 3 inch That's 6 inch. That's half foot. And I already have 5 in here. So this will be over a width of 4.5. So that's 4.5 times 12. That's B for this one, where the longitudinal steel will be furnished or provided. Times 12, that's H, because it's BH. How much this? How much?
1.3.
Inch square. Is this per foot? No. That's all what you need. That's all what you need. Okay? If we use number 4 at 12, if we use number 4 at 12, how many bars we need? Or how many bars of number 4 we need? What's the area of number 4? Area of number 4. How much? Point? Area of 1, 2?
Area of 1 number 4?
Yeah, area of 1 bar number 4.
0.2. We would need 7 for that.
0.2. So we need, so 1.3 divided by 0.2 equal 6.5?
Yeah.
6.5. Use 7 number 4. 7 number 4. What's the spacing between them? 7 bars in the longitudinal direction. The width that they will occupy is 4.5. 7 bars, how many spacing they give you? 6.
Why are there no bars underneath the wall? Like, why are we still using 4.5? Oh, it's the cover that we're, never mind.
I
Okay.
don't understand the point.
The 4.5 is the cover on each
Where are
side.
those going to come? Here, right?
Going that direction.
In the wrong direction.
Yes.
Can I get this one closer than 3 inch to this side? This one? So that's 3 inch gun. Can I get this one, the first one I'm going to put here, closer than 3 inch? 3 inch is gone.
Oh.
So 5 minus 3, 3,
Okay.
which is half foot. So that's, this distance from here to here is 4.5 foot times 12, an inch. Okay? So the 7 bars, when you put 7 bars, how many spacing you create? 6 spacings. So 4.5 times 12, that's the width in inch. Divided by 6. So this will be number 4 at 9. Don't worry, just tell the guy put 7 bars. Some will be like 10, some will be 9, some will be 8. Not a big deal, I mean. Or 8.5. 7 to their best in that direction. Okay? 7 to their best in that direction. They do a good job. Usually, guys, the foundation and the columns really, they take good care to make sure they are concentric. Everything is fine. The column is exactly in the center. Okay, they measure it really nice. Because you can't, I mean, once you have the foundation, usually the building up is so fast. You spend some time excavating, cleaning things, doing all of this civil thing around drainage, columns, center lines of the columns, center line of the footing, all this. Once you have it, it's just, they put things together. Good? So that's what we have. So those are 7 of them. Let's say this is 7. 7, number 4. Okay, for string length. That's the design. That's the design. Sometimes you may provide, sometimes you will say something like, you will see one at the top here, because when we want to tie this one, this reinforcement to the wall, okay, we need something also at the top here to have it connected or so it doesn't move. You may have like one every 2 feet for tying those bars in the footing. Remember, this wall will have reinforcement going down, right? The wall or a column will have reinforcements, right? You may have 1 layer or 2 layers. So this reinforcement will go down, will be planted in the footing. This will be planted in the footing, right? How much you plant this one in the footing? Development. So you calculate the development link for this bar with the conditions you have. Normal weight concrete, not epoxy coated bars, all of these things, the size of the bar, it's not going to be top or bottom, these coefficients, you calculate, let's say you needed like 30 inch, or this one. Okay, you see, is this enough or not? If not, you go hooked. You hook this one not to this side, you take this one to this side, you take this one to this side. So you have enough within. Remember, this, is it in compression or in tension? Bar in compression or in tension? Wall is a compression member, so usually you don't need 30. You need a very small thickness. Okay?
At the top of the footing, when we tie it together, does it matter? Can we just use number 3s every time?
By the way, this is for constructability. Now what they do usually, what they do usually, you see this one? It's every 9 or whatever. Yeah, that's the data show. It's every 9 foot. Is it this one? Number 4 at what?
9 inches?
At 9.
Yeah.
So every other 9, one of them they take it all around.
Oh, okay.
What?
All around.
Oh, okay.
Like every 3, depending on how heavy the steel there, they will do not everywhere. Let's say every 3 spacing. We said there's one here, right? Then 9 inch there is another one. 9 inch there is another one, right? 9 inch there is another one. So they will start with the first one. You say to tie this reinforcement here, we will do that. We'll take it and we make it closed rectangle. So they tie the bars here. Like that. They skip the second, third, or whatever, then they go with the one. For constructability, not needed for constructability. Good? That's the design of wall footing. Any question on this? So you know how to design a wall footing now? I will start with an introduction, 10-15 minutes about for single column footing. We'll take example. I will start with the example. Then we continue next lecture. There's one more lecture, it's a solid lecture that's left, in addition to the presentation you have. So, should be able to finish the footings. Example. Now this example on, again I'm going to cover single column footing. So the column is column 18 inch by 18 inch square. F prime C will be 4 KSI, Fy 60 KSI. Dead load 5 kips. Live load equal 175 kips. Q allowable 5 KSF.
And does that correspond to a depth?
Q allowable doesn't correspond to the depth. Sorry. Q allowable is at the level of the footing. At the level of the footing. Level of footing equal 5 feet. So this is Q allowable at 5 feet. At 5 feet. Design a footing for this column. Design a footing for this column. Steps, if you guys like the steps. 1. A equal 225 plus 175. I need two guys fast with the calculation. Over. Even before we do that. Q effective equal 5 minus 5 times 125. Q effective will be 5 minus 5 feet of average concrete and soil. Take it 0.125, as I said. So how much the top one?
4.37.
4.375. Yeah? Kip per foot square or KSF. So A will be the service load divided by Q effective, which is 4.375. You get A 91 foot square. So the dimensions B equal H for the footing, because it's single column footing and it's a square footing. That's our footing, 1.5 foot. That's our column, and that's the footing. So this equal that. So how much take the square root of that? This is the area, which is a square. So each side is how much? 9.6. 9.6 foot. Use 10 foot. We will use 10 foot. So this will be 10, and this will be 10. Good? This will be 10, and this will be 10. Remember, the cross section will look like this. This is the column, with the loads coming from the column. The width of the column is 1.5 feet, and this width here is 10 feet, and this is H. This is H. We will have, now, the reinforcement. How does it look like? This is a cross section through the column. This is a cross section here. I took a cross section, I'm looking at this. This is H, I need to design. There will be reinforcement. You think the reinforcement need to be in both directions?
Yes.
Of course, so there will be reinforcement needed in each direction. So this and that. And they are both flexural. Both flexural. You know what's the assumption in the single column footing? That the footing is fixed at the face of the column in each direction. So the footing is fixed here and fixed here. The footing is fixed here and fixed here. Okay? You get questions like that in the FE, Spencer?
Yeah.
Good? You get a question like that. They ask you about the punching sheet, which I'm going to tell you in a minute.
Not yet.
Did not?
Ours were much simpler, I guess. Very.
You just took it, right? You just took it?
I took mine last month, yeah.
You just took this like 2 days ago. 2 days ago, right? And you said there's a lot of concrete. Okay.
First chapter stuff.
Now, for this one, they have good questions about the foundation. Not easy questions, actually. Okay, that's the thing. So the first, but look, there's 2 types of shear in the single column footing. This is the hard one. There's 2 types of shear. There is something, as we said, as I told you, there is something, the shear at D from the face of the column. Right? So how much this distance from here to here will be? Guys, this one should not be confused. Look how you do it fast. 10 minus 1.5 divided by 2. 10 minus 1.5 divided by 2. So this? 4? 2.5?
Yep.
So this is we have. We said the critical section for shear, I expect you to know, is at D from the face of the column. Right? At D from the face of the column. We don't have D. That shear, you know what's called? This shear that we deal with, this at D from the face of the, you know what they call it? They call it the one-way shear or the beam shear. It's like the shear in the beams. So they call it one-way shear or beam shear. There's something else. There's something called punching. Sometimes the column loads are, if they are high and the footing underneath it is shallow or small thickness, the column may punch the footing. or may cause cracking in the footing. So this one may, like with this load, break it somehow. If it's gonna punch it, you know what's gonna happen? The cracks will develop over 45 degrees. They crack it like that. They chop this piece such that the distance from here to here, don't try. The distance from here to here is D. Wait. The distance from here to here. So when this one is chopped and you measure it from the bottom, it's the column plus D. Okay? Typical. Or HH, D and D. But to the center now, if you want to calculate the strength to this, under the top is 0, right? So to the center here will be, this distance from here to here is how much? D over 2. So the critical section for that punching is all around. It's going to punch it all around. That box will go like that. How much this distance from here to here? D over 2 all around on the four faces. D over 2 from the face of the column. That's we call the perimeter for punching. The perimeter for punching. They have this designation for it. B naught. You guys tell me what B naught equal now. 4 times each side. Right? 4. I have 4 of them for a square column. I have 4. This length. I have 4 times D plus. So this is D and a half. This is D and a half. So both are D. And this is the length of the column, or the width of the column. Okay? Column. Width. If it's square. If it's not square, it will be like H plus D in one direction, 2 of them, right? Then you have B plus D, 2 of them. It's just a length, calculating the perimeter length. Right? This is called B naught. This is the section for punching. Let me back up now a little bit. We said this beam shear at D from face of the support, the shear when you calculate at D from face of the support, we compared with PVC, right? We compared that with PVC. That PVC was equal to what, guys? 0.75 to square root of prime C BD. The guys found that from lab experiments that the strength of the foundation for punching is way more than 2 square root of prime C BD. So the strength of the footing in resisting the punching, that is the load within that box, is 175 times 4 square root of prime C B naught D. So PVC punching equal 175 times, look at the 4, big 4, square root of prime C, big B naught D.
What about lambda?
Lambda, that's a normal weight factor. If the footing is, a lightweight factor. Lambda is 1 for normal weight concrete. Lambda equal 0.8 or 0.85 or whatever for factor when you have lightweight concrete. It's specified. Sometimes 175, depending on the unit weight of that lightweight concrete. Okay? So this is available for you. The only thing you need is this one. Again, now we have the area. What do we need to design? D. Once we have D, we can calculate the moment and find the steel. The structural design is so easy. The only thing we need to find, D. In the FE exam questions, the one that I read, they ask you, check how much the punching shear strength. Basically, they're asking you to calculate this one. They give you D and everything. You just need to find B naught and do this multiplication. Okay? So in our case here, the only item we need is D. D. If we assume D, we can calculate V ultimate from the one-way shear or the punching shear. We're going to call it V ultimate 1 and V ultimate 2. This is for punching and this is for the beam shear. Okay? We're going to calculate those shear forces. Then check if this is bigger than that or not. So we're going to assume D, calculate this, compare it with that in single footings punching shear control. So you determine D based on punching. You check the one-way shear, and usually it's good. Okay? In the combined footing, one-way shear or the beam shear control the design. The punching doesn't control the design. In the wall footing, no punching. Okay? Good? So this is what we need to calculate. So as I told you, in the design of the footing, you need to assume D. So in your mind, you will say, you know what? Yeah, I mean, it's not going to be more than 2 feet, maybe 2.5 feet, 3 feet deep footing, that's deep. So you may start with like 2 feet depth and check. If you have h equal 2 feet, which is 24 inch, right? Now, how much you subtract to get D? Now, check with it, guys. We have this steel and this steel at the top. They're supposed to do the same job. They have to do the same job. They're supposed to resist the same moment. So what you do, you design one and you make it the rest. You design one and you use it in both ways.
You don't weave them?
That's how you put it. But when you design one of them, then the other direction is exactly the same. It's a square footing. So which one is more critical? The one with the smaller d, which is the one at the top. So d will be h minus 3 minus the diameter of this guy minus half the diameter of this guy. If you have number 8, then you will have 3 plus 1 plus half. If you have like number 4 as we're getting, or number 5 or number 6, let's say, it's going to be like 4 inch. You understand what I'm saying? If you use like, you know, assume that we're going to use number 6, right? Which is 6/8. That's 6/8 plus 3/8, half of it is about 1 inch. So roughly you can have h minus 4 if you want, or h minus 4.5 to be in the safe side.
Does there need to be any distance between the actual steel?
They're sitting with each other.
They sit right on each
Yeah,
other?
like it's a mesh like that.
Okay,
Yep, and they are connected to each other at the corners.
okay.
Okay? So we're going to assume D. Try H, if you want to check this one. Try H equal 24. D will be 19.5. If you want to take it, 19.5 to be conservative. Once you have 19.5, that's your D. Here, 19.5 plus 18 times 4, that's B naught. 19.5 plus that times 4, this will give you this one in inch. In 175 times 4 times square root of 4,000 times that, divided by 1,000 to get it in K. Okay? Now what's VU2? The last thing I'm going to, this is the hardest one. You know what's VU2? Look what's happening. I'll try my best. So it's going to punch it, right? When it's punched, it's going to look like this. This is gun. Right? This is gun. Twin. Where it is? Here. This piece. It's chopped, right? What's on top of it? Is the column. This is your column, right? Twin through it. This is what you have. So this is a gap here. It's gone. I'm doing the 3-by diagram. So you know what's at the bottom? You know what's at the bottom? Q ultimate, right? Q ultimate at the bottom. Is there any Q ultimate here? It is there. And there is what here? P ultimate. So P ultimate and Q ultimate. Do you have this dimension? Yes. D plus column. D plus column. So we have it. We have this by that. It's not a perimeter anymore. So we have this and we have that. So where is the punching resistant now? Where is the strength now? Where is the punching shear strength? It is what's resisted this one from being chopped. It's what's resisting this one from being sheared. So where it is now? Where it is? Shear stress, where? So the shear stress times this area on the 4 faces, okay, is give you a shear strength up resist the difference between them. In other words, you know what's VU2? You know what's VU2? It's P ultimate minus Q ultimate times that. Or make your life easy. It's this. Because this one, you know what it is? It's on the inside face in the other direction. Look, VU2, I say VU2 will be equal. Look, please don't try. Will be equal. Q ultimate times the area. Q ultimate times A minus area inside. The taken area. Because this equal that. So if you take the full area, you subtract this area from it, that's VU2.
But it has a different area at the top and the bottom. Isn't that a slant?
That's what we did. D over 2. We said 0 D. We took the average. D over 2.
The average. Okay.
Yeah.
Okay.
Yeah. Not many guys know why D over 2.
Now we do.
Okay, guys? So VU2 Q ultimate times the area minus, not B naught. Some guy will multiply by B naught square for some reason. B naught square doesn't mean anything. It's that width times that. For the area now. It's equal to this minus Q ultimate times this area. Good, Andrew? Okay, so I will see you next Monday. Yeah, see you next Monday.
You want to come in this week?
Yeah, going with you guys. Oh, yeah. Yeah, I will see you tomorrow, I think. We'll arrive tonight, I think. But I will see you on.
You're already in bed with us on the weekend.
I'm not gonna touch
I was
these.
thinking,
Just turn it off.
No, I'm not gonna.
Just turn it off. How do you do this,
How do you do this?
Oh, he flipped it so I can see it.
And then he said to take this to the studio, and then he can take out the video because he cannot do it. Like, and he's gonna make you a